Let's quickly look at the convolution sum. Again, here we have a discrete time system described by h sub n, where h sub n is the impulse response. Again, our arbitrary input is described by this sequence for this example, and our corresponding impulse response due to a single impulse is described by this h-n. We have our input sequence decomposed into a time-weighted shifted impulse, and our output is described in terms of a weighted sum of impulse responses. Again, our input is decomposed into these series of impulses. It's weighted and time shifted, described by this equation here, where we substitute our x0, x1, and x2 by the corresponding impulses that are weighted and time shifted. Now we're going to show you two procedures on how to evaluate this convolution sum. The first is a little bit simpler version in which I'll put it in tabular form and taking advantage of the time invariance system approach, and the other one is a formal procedure in which we do time reverse and shift, integrate, multiply, and then integrate procedure. But that will be discussed in this second part. First, I'll show you the tabular form so you know what's going on, and it results in this process right here where we have arbitrary input n. Here's our corresponding impulse response due to a single impulse that has unit magnitude. Here we'll evaluate n equals 0 to 4. We'll see why. And we'll start off with our first input as a result of this impulse with a weight of 3. And because it's weight in a later slide, and this sum is also called the Discrete-Time tripled convolution. So where there's a 2, there's a 6. Where there's a 1, there's a 3. And when there's a 3, there's a 9, as shown here, with no time shift. Now, let's look at the second part of this sequence, with the weight of 2 shifted by 1. Well, if it's shifted by 1 with a weight of 2, this impulse response will be shifted by 1, and we double the input. So this is shown right here. We have a 0 in this, where n equals 0, and we have a corresponding output due to x1 resulting from this, and we could see that it's shifted by 1 and doubling the weights from here. So 4, 2, and 6. Likewise, the next one at 2, we call this x2 at k equals 2 for n. We have y2n for x2 of n equal, where it's shifted by 2. That's why there's a 0 in here, and has a weight of 1. So we'll just keep these numbers right here, 2, 1, 3. So this is the three outputs as a result of these individual impulses located at 0, 1, and 2. Adding these, due to the superposition and linearity property associated with this system, we get 6, 7, 13, 7, and 6 at the corresponding ends right here. So adding up all those inputs, we get an equivalent mathematical description of 6 delta n at n, 7 delta at n minus 1, 13 at delta n minus 2, 7 with an impulse located at n minus 3, and a weight of 3 located for this impulse at n equal 4. So that's the mathematical description. Hopefully you see we both use the linearity as a result of the superposition and the time shift resulting from the time invariance property, where the impulse response just changes when we shift the input and weigh the input. Okay, so that's the first process. A bit more formal approach. So here we're given the same problem, and we should get the same result as described in the book. So here we have h sub n. Now we want to apply this equation here, so we'll look at this h sub minus k right here. So this is just a reverse or reflection reflected version of 8 sub n, and then we n where we shifted far to the left to get this. Okay, notice at where the weight is 3 here and at minus 2 we change it to n minus 2. Where there's the 1 here we go n minus 1, and when then there's a 0 here we go to n. So that's the first part of evaluating this convolution sum, where we have hn minus k described by this sequence here now in this example. Okay, now we're take this convolution sum and we're gonna convolve it with this x sub k. Okay, with the first process we're gonna see the first overlap as we shift this 8 sub n to the right. We'll see this 2 at n when n is equal to 0 overlap with this 3. And so that's the first overlap, and so that's 2 times 3 equals 6 at n equals 0. So when we substitute n equals 0 we get this overlap. Now when is n equal 1 we're going to shift this again to the right and we get the corresponding function right here where the 2 and this 2 overlaps as shown here, and this 1 and 3 will overlap as shown here, and this is the shifted when we substitute n equal 1. So this will be at 1, so this 2 will be at 1, this 1 will equal 0 as shown here, and this when n is equal to 1 this is 3 is located at negative 1. So we could see here it's 3 times 1 as shown by this process plus 2 times 2. Okay, 1 times 3 plus 2 times 2 is equal to 7. So that's for n equal 1. The next one is when n equals 2 we're going to get overlap of these 3 impulses with these 3. Okay, that's shown here where the 3 and 3 overlap, the 1 and the 2 overlap, and the 2 and 1 overlap. So 3 times 3, 1 times 2, and then 2 times 1 right here, and that's a sum of 13. Likewise for n equal 3 we'll see that the 3 will move into here for this 8 sub n minus k when n is equal to 3. So when this 3 will be located at 1 shown here, and then this 1 will be located at 2, and then this 2 will be located at 1 at 3 well, when n is 3 at 3, I'm sorry, 3 right here, 2. So the only overlaps is this 3 times 2 and 1 times 1 shown in this equation, which yields 7. And then finally we have one final overlap, and that's shown here. So when n equals 4 this 3 will be located at 2 overlapping with this 1. This 1 will be located at 3, and this one for hn minus k where n is equal to 4 for this n equal 4 shown here for this 2. So the only overlap is this 3 and 1. Okay, and finally representing all the functions that we had earlier we get the same result as we did with the tabular form, but this is more a formal approach in which we reflect and then shift and then multiply and then add. That's what this convolution sum procedure is all about. And we'll see that's useful when we talk about the convolution integral.